Today's lesson is on using 0 as an exponent and using negatives as exponent, negative integers. So this is in the textbook, Chapter 1, Section 5, and you can start on page 40 in your text if you want to follow along and do this with me. I would like you to copy this chart into your spiral, please, and fill this in with me and answer a couple of these questions in your spiral with me. So on page 40 in the text, and have your spirals open. So number 1 says, let's understand the 0 property. Use the power of a quotient property to simplify each expression. Write the quotient as an exponent. So 3 to the 5th over 3 to the 2nd, we know that keep the base and subtract the exponents would be 3 to the 3rd. So 3 to the 5th over 3 to the 3rd, keep that base of 3 and subtract the exponents. 5 take away 3 would be 3 to the 2nd. 3 to the 5th over 3 to the 4th, keep that base of 3. 5 take away 4 would be 3 to the 1st. So 3 to the 5th over 3 to the 5th, keep that base. 5 take away 5, that would be 3 to the 0. So it says, what expression did you write in for 3 to the 5th over 3 to the 5th? Well, I wrote in 3 to the 0. What exponent did you use? I used the exponent 0. In factored form, the quotient of 3 to the 5th over to 3 to the 5th is using 3 as a factor 5 times in the numerator, using 3 as a factor 5 times in the denominator. If you divide out all the common factors, well, I'm going to do that here. I can cancel from numerator to denominator. I have only 1 over 1 left. What is the value of 3 to the 5th over 3 to the 5th? Well, it's 1 over 1, which equals 1. Yes, so what do you, based on my findings here, what can you conclude about 3 to the 0? Which is equal to 3 to the 5th over 3 to the 5th. Keep the base, subtract the exponents, you get 3 to the 0. That value is 1. So I would like you to take a moment in your spiral and make a prediction about the value of any number raised to the 0 power. Then use a calculator to check your prediction. Any number raised to the 0 power. Then use a calculator to check your prediction for several numbers. For example, to raise the number -2 to the 0 power, you can enter these keystrokes. Does your prediction hold true? So write something down in your spiral. What do you think about any number raised to the 0 power? What do you think its value is going to be? If it's a negative base, do you think it's going to be -1? And if it's a positive base, will it be +1? What if it's a rational number? What if it's irrational? Let's try some of those. So I'm going to get out my calculator. Oh, better clear some things here. Clear. So I'm going to try some of those. In fact, I'm going to try that example that it said there, -2 raised to the 0 power. To do this on our calculators, the negative base has to be in parentheses, so I'm going to use the parenthesis key, -2, close the parenthesis. The power key is that caret button that you see there, raised to the 0 power. So let's think. Our negative base raised to the 0, will the answer be -1 or +1? Oh, +1. So -2 raised to the 0 power equals 1. It says try any number. What if we try a rational number? How about something like, oh, let's say 47 hundredths. Put it in parentheses, hit my power key, raise to the 0 power. Is it going to be a decimal answer? No, it's going to be 1. So 47 hundredths, a rational number, which -2 is an integer, also a rational number. Rational numbers raised to the 0 power equal 1. What about an irrational number? Let's try an irrational number like the square root of 13. It's irrational. Close that parentheses. Toggle off of that. Raised to the 0 power. Enter. Oh, syntax error. What did I do wrong there? Let's see. Oh, I didn't toggle off soon enough. So let's do that again. Parenthesis, start over. So parenthesis, square root, 13. So toggle off that right here. Then close the parenthesis. So the square root of 13, an irrational number raised to the 0 power. So that equals 1. So if it says syntax error, you put something in the calculator wrong. That's you, the person, doing something wrong. An irrational base like 13 raised to the 0 power, that equals 1. Let's try another irrational. Let's just check. What's the most famous irrational number? Pi. Let's do pi. Pi. Ooh, pi. Close the parenthesis. Raised to the 0 power. Enter. Ooh, pi to the 0 power. Most famous irrational number. That equals 1. Tried a negative. I tried a rational. Tried some irrationals. I bet any number raised to the 0 power is going to equal 1. Let's think about that. So let's go back to our notes. Examples for your spiral. Simplify each expression and evaluate where applicable. Well, there's an important note start down here. A non-zero number. Non-zero. So we can't say any number because it says a non-zero number, meaning not 0. A non-zero number raised to the 0 power is equal to 1. So it can be any real number, I'm assuming, raised, except for 0, raised to the 0 power. Why can't it be 0 here? Why can't it be 0? Okay, well, let's say that we have our a to the 0 power, like it says here. Copy this into your notes. Would have to equal some a to the nth over a to the nth, right? Because that would equal a to the n minus n, which would give me 0. Okay, so now let's say our base is 0. Okay, so 0 a to the 0 power would then have to equal, okay, a to the nth over a to the nth, just like we did here. But if it's 0, I would have 0 to the nth over 0 to the nth. Can we do that? Can we have 0 in the denominator? Can we do this? Can we do 0 divided by 0? Division by 0 is undefined. So no, because of the quotient of a power rule that says keep the base and subtract the exponents, if 0 is the base, it would have to go into a denominator, and you can't do this. This is undefined. So any non-zero number, back to our rule over here, only any non-zero base raised to the 0 power will equal 1. Cannot use 0. So that's important. No, some good thoughts there. So let's go back to our expression simplification here. So we have several examples. I think I have 5 of them for you to, 7 of them, excuse me, 7 of them that we're going to copy into our spiral. I'm going to do some of them with you. You're going to do some on your own. So simplify each expression and evaluate where applicable. Where applicable. So 7 to the 3rd times 7 to the 0, keep the base, add the exponents. That's one way I could do it. 3 plus 0 is 3. Or I could say, oh, 7 to the 3rd, well, I know 7 to the 0 is 1. Any number times 1 is just going to give me that any number, 7 to the 3rd. So a couple ways you could do number 1. Number 2. Well, they don't have the same base. This is expanded notation. This is a definitely evaluate question. This is 1 times 100, 10 squared, plus 2 times 10 to the first, that's 10, plus 3 times 10 to the 0, well, that's 3 times 1. So I have 1 times 100, that's 100, plus 2 times 10, that's 20, plus 3 times 1, that's 3. 100 plus 20 plus 3, well, this is an evaluate where applicable question. That equals 123. Number 3. 4 to the second times 4 to the sixth over 4 to the eighth. Well, we know how to simplify these. We've already done this. This is 4 to the, keep the base, add the exponents, over 4 to the eighth. Well, any number divided by itself is going to equal 1. That's one way I know this expression is 1. Or, using my laws of exponents, I could say, oh, that's the same thing as 4 to the eighth minus eighth, keep the base, subtract the exponents. Well, that's just going to be 4 to the 0. Well, that's just going to equal 1. So it did say to simplify where applicable, you know, evaluate it. So yes, this answer is 1. If it didn't say evaluate where applicable, and it said simplify each expression, leave it in exponent form, then I would answer it as 4 to the 0. Evaluate where applicable, the answer is 1. Any number divided by itself, I knew this was going to end up being 1 anyway, though. Even using my laws of exponents, I knew I was going to get it down to 4 to the 0, which equals 1. Number 4, a to the fourth divided by a to the 0. Well, I'm going to change that to a to the fourth divided by 1, because that's going to help here, which is just a to the fourth times a to the third. Well, this just equals a to the fourth times a to the third. Keep the base and add the exponents. I get a to the seventh. Another way I could have done this is I could have said, oh, okay, well, a to the fourth divided by a to the 0, keep the base and subtract the exponents. 4 take away 0 is just 4 times a to the third. I could have done it that way, too, to get a to the 7th. So either way, I could change this into 1, or I could use my quotient rule that says keep the base and subtract the exponents. Either way, try these, evaluate where applicable. So I'm going to let you try these on your own, and this is definitely a evaluate where applicable question, little hint there. So try number 5, 6, and 7 on your own, and we'll go over those in class. So a closing question for the first part of these notes. We're going to go on here. I'm going to keep going, but here's a closing question for 0 exponents, using 0 as an exponent. If 10 to the third is 1,000 and 10 to the second is 100, then how do you represent 10? Well, we know that. 10 is 10 to the first, and 1 with an exponent. Oh, our place value. Yes, 1 is equal to 10 to the 0, the ones place. We are a base 10 numeral system. That's what this is talking about. The ones place value is 10 to the 0. The tens place value is 10 to the first. The hundreds place value is 10 to the second. The thousands place value is 10 to the third. The 10,000s, and you can keep going with this, that's 10 to the fourth. Do you see that there are no zeros in the ones place? I wonder if this exponent has something to do with no zeros in the ones place. There is 1 0 in 10. There are 2 zeros in 100. There are 3 zeros in 1,000. There are 4 zeros in 10,000. There are 6 zeros in 1,000,000. I think those are related. Yes, they are. So that's it for the first part of the notes. The second part of the notes talking about negative exponents. So this is part 2. We're going to also talk about negative exponents. And this is in your text on page 43. Follow along on page 43, negative exponents. Use the quotient of powers property to simplify each expression. Hey, just like we did before. So yes, I would like you to copy this table into your notes, into your spiral, and it says 4 to the 5th over 4 cubed, keep the base, subtract the exponents, I'd get 4 to the 2nd. 4 to the 5th over 4 to the 4th, keep the base 4, and subtract the exponents, I'd get 4 to the 1st, which equals 4. 4 to the 5th over 4 to the 5th, keep the base, subtract the exponents, 5 take away 5, I'd get 4 to the 0. Well, that equals 1. 4 to the 5th over 4 to the 6th, keep the base and subtract those exponents. 5 take away 6, that's negative 1. That equals 1/4. I'm dividing by 4 here as I go along this pattern. Maybe you've seen that. 16 divided by 4 gives me 4. 4 divided by 4 gives me 1. 1 divided by 4 gives me 1 divided by 4, 1/4. And 1/4 divided by 4, 4 to the 5th over 4 to the 7th. Keep the base and subtract the exponents. I have 2 extra 4s in this denominator. Yeah, 2 extra 4s. 4 times 4 in the denominator does give me 1/16, 4 to the negative 2nd. What expression did you write for 4 to the 5th over 4 to the 6th? I wrote 4 to the negative 1st. What exponent did I use? I used -1. So I answered these 2 questions here. In factored form, the quotient 4 to the 5th over 4 to the 6th, 4 is used as a base 5 times in the numerator, and 4 is used as a base 6 times in the denominator. Well, I can cancel from numerator to denominator, and I get 1/4 left in the denominator. So what's the value of that? 1/4. So repeat step 3. Step 3 says repeat step 2 for 4 to the 5th over 4 to the 7th. What is the value of it? Well, I end up having, yes, 5 of them, as you saw at first, and 7 in the denominator. So like I said, I'm going to have 2 extra ones in the denominator. Yep. And I get, so I'm repeating the steps, I get 1/4 squared, which is 1/16. Suppose A represents a non-zero number. How would you write A to the negative 3rd using a positive exponent? Well, I would do this. I would say it equals 1/A to the 3rd. That's A to the negative 3rd. Just like 4 to the negative 2nd here was the same thing as 1/4 to the 2nd, which was the same thing as, if I evaluate that, 1/16. So a negative exponent means reciprocal. Did you catch that? 4 to the negative 2nd is 1/16. 4 to the positive 2nd is 16. So negative exponents don't have to do with negative numbers. They have to do with the multiplicative inverse, or the reciprocal, as you call it, which that word I don't like. So here's some examples. Rewrite with a positive exponent. So A to the negative 2nd is the same thing as the reciprocal of A to the 2nd, or the multiplicative inverse. Well, this would be A to the 2nd over 1, flip it over. 1/A to the 2nd. That's what I mean by multiplicative inverse, or what you call reciprocal. 5 to the negative 3rd, think 5 to the 3rd and do its multiplicative inverse. That would be 1/5 to the 3rd. 2x to the negative 4th, keep that base in parentheses. That would be, think positive, do the multiplicative inverse. 1/2x to the 4th power. Negative 8, watch that base, it is negative, so I'm going to keep it in parentheses. Think positive. Negative 8 to the positive second power. Now do the multiplicative inverse. It would be 1 over negative 8 to the 1 over negative 8 to the second power in the denominator. Make it positive. So, thinking about that multiplicative inverse idea, 3, well, that's like really having an m to the 0. It's times 1, right? Could think of it this way. This is one way I could think of it. It really has like an m to the 0 on it, which is really just 1. 3 times 1 is just 3. I could put an m to the 0 up there. I could. So I could say, oh, okay, well, that's 3. And to keep the common base, subtract the exponents. Ooh, that's a negative 2. M to the 0 minus negative 2. Well, we'd have to change that to adding the opposite. And we'd get 3m to the second power. How would that become positive? Well, if I did the reciprocal of something in the denominator, doesn't it go up to the numerator? The multiplicative inverse of this would be, because this is like being 1 over m to the negative second. Think positive and reciprocate it. Or do the multiplicative inverse, which would be 3 times m to the second over 1, which is 3m to the second. So there's a couple ways you could think about that. I could put in that, what you don't see here, it's not magic, m to the 0 power. In fact, any number really has a variable to the 0 power on it. 7 is the same thing as 7x to the 0 power. That means 7. I could put a, negative 18. That could be b to the 0 power sitting next to it. It's not there, but I could put it there. It still means negative 18. We don't usually do that, though. We don't put 0 powers on variables. But I could, because it just means 1. Or I could think of, how do I make something that's negative in the denominator its multiplicative inverse? Well, I make it positive and move it up to the numerator. If it's in the numerator already, like number 4, that's really negative 8 to the negative second power over 1. Well, if I do the multiplicative inverse, it goes down to the denominator and becomes positive. So for a variable with a negative exponent to be shown as a positive exponent, it literally moves from numerator to denominator, or denominator to numerator. Kind of confusing. Let it sink in for a minute. Simplify each expression below. Use positive exponents. Oh, okay, it says you have to use positive exponents, so you can't leave anything with a negative exponent. That's always best standard form. Always answering with a positive exponent. Might not say that in the direction, but that is the standard form of an exponent answer. So 13 to the negative 4th times 13 to the 7th. Well, I could do this 2 ways. I could say, oh, you know what? I want that to be positive, so I'm going to drop it to the denominator, do the multiplicative inverse of it, times 13 to the 7th. Well, that gives me 13 to the 7th over 13 to the 4th. Keep the base, subtract the exponents. That's 13 to the 3rd. Or, easier way to do that, I could use my product of a power rule and say, oh, keep the base and add the exponents, negative 4 plus 7. Whoops, I want to have a big parenthesis there. Keep the base and the exponents, which is generally how I do it. I don't do this step usually. I just say, oh, okay. Just like if that was a positive 4, I would say 4 plus 7 is 11. Well, it's a negative 4 plus 7. Keep the base, add the exponents. Okay, negative 4 plus 7. 3. That's the better way. This is the way that I like to do it. Keep the base and add the exponents. However, you could, again, like in number 2 here, you could say, oh, okay, make this into the multiplicative inverse that it is. And it would be 1 over x to the 7th times 1 over x to the 4th, right? This is in the denominator. Leave it down there. Well, that's 1 over x to the 11th. The other way that I could do this is I could say, okay, keep the base, subtract the exponents. Ooh, be careful. That's negative 7 minus 4. Oh, that's x to the negative 11th. But it said right as a positive exponent. So I would have to drop this to the denominator, do the multiplicative inverse of it, and say 1 over x to the 11th. So I could do it either way, but I'm going to still get the same answer, 1 over x to the 11th, because I have to answer with a positive exponent. So 9m divided by 3m to the negative 2nd, well, I like it written about that division symbol. Okay, well, 9 divided by 3, I can factor that. That's 3. And m to the 1st minus negative 2. Okay, be careful. Keep the base and subtract those exponents. I'm going to get 3 to the m, 3m to the, okay, so that changing that to adding the opposite, 1 plus 2 makes 3, so I'm going to get 3 to the 3rd. Be very careful when you have subtracting with a negative. We know that we have to change that to add the opposite. So 3m to the 3rd would be the answer to number 3. Now I know this is a little tricky, but I would like you to try number 4, 5, and 6 on your own. So we'll go over those other 3 that were on the earlier part of the notes, and we will go over these 3. Give it your best shot. You can open your textbook and help. And we will go over these in class tomorrow.